In this last subtopic, we're going to look at the method of converting electrical signals to optical signals. So we're going to look at an LED and we're going to look at a laser diode, a couple of calculations, and then we're going to look very briefly at the encoders and decoders involved. So the first thing we're going to look at is our LED. It is a PN junction, and we're going to look at semiconductor material in the last overall topic. The N, if we draw it, have our LED. So as we've already discussed, our LED has a wider range of frequencies. Our LED battery it emits lots of different colours. The P&N type materials will come across in the next subtopic. So our P type material has got a deficit of electrons in the outer orbit, and the N type material has a surplus of electrons in the outer orbit. So if we now move on to a laser diode, it actually is quite similar to an LED. It's a high power device, so we're going to need a heat sink. Okay, so if we now move on to looking at some comparison between an LED and a laser, we can create a little table. So relative to each other, then LED is going to be a low cost option compared to our laser. The power of our LED is also low compared to our laser. Speed low, and again high. Frequency range that we've got is high, and laser, we've got a nice tight frequency range, but transmitted distance, we've got a long distance with our laser, but only a short distance with our LED. So in essence, our LED has got a broad beam, it's got less power, so therefore limits its use in multi-mode. Whereas actually our LED it's robust, plus it has a long life and efficient. But a laser has a high switching, which has a good data rate, so therefore we would use it in multi-mode fibers. So if we look at a couple of calculations now referring to our energy and power, so E energy in joules, power in watts, and time in seconds. Okay, so if we're looking at the power delivered, then so power is equal to energy divided by time. So we've got a 20 millijoule laser, and we're going to power it for 4 milliseconds. So therefore we're going to have 5 watts. Okay, so we've got a different laser this time, outputting 3 watts, 7,000 pulses per second, and each pulse is 150 nanoseconds. So we want to know what the peak power delivered with each pulse. Okay, so the first thing we need to do is look at what our energy that we've got. So we've got 3 watts. Sorry, I beg your pardon. Let's start off with writing the equation. The energy for each pulse, then we've got 3 watts of energy, and we've got 7,000 pulses. So therefore each pulse has 428.6 microjoules of energy. We then look at how much energy is delivered in 150 nanoseconds. We have 2.86 kilowatts. Okay, in this last section we'll look at encoders and decoders, starting off with an encoder. Therefore, encoder is quite simply we're looking to convert our electrical energy into light energy. So we've got two circuits that can do this, one using a transistor and one using a MOSFET. Okay, so we've got our two circuits, just using a transistor and MOSFET in both of them. Remember that on our transistor circuit we need a resistor on the base there to control the current, because current control device, and we also need, in both examples, we need a safety resistor to go with our LED here to avoid excess current flowing through it. But with our MOSFET voltage control device, we don't need a resistor there on the gate. Okay, so we'll focus on our decoders now. So we've got our light energy a bit transmitted, so we need to convert that back into electrical energy. We've got our first circuit, which is our photodiode circuit. Note here that the photodiode is in reverse bias. Okay, so when we get light on our photodiode, we then get a current in the base, which switches the transistor on so it conducts, so the voltage at the input to the Smith trigger goes low, so the output from the Smith trigger goes high. So our last circuit is an op-amp detector, still using a photodiode, and see that provided the output isn't saturated, then both input terminals of the op-amp are equal to the same voltage. So then the voltage drop across RF is I times RF, which would then give us our voltage out. So a question along this sort of line would be just to work out what V out would be. So therefore we've got 20k times by 400 microamps gives us a output voltage of 8 volts. I times R.